Hey, let's start. Yes, this is the second class. We will continue our discussion on solar to X, but today we'll focus on fuels, turning solar energy into liquid fuels or gaseous fuels. And I would like to start here where I show that solar energy doesn't have to be utilized only in the form of electricity. It can be utilized in the form of heat, in the form of turning it into chemicals energy. It can be converted to different form. For example, electricity, and then store it in the batteries, or convert it into thermal energy, and then thermal energy then convert it again into chemicals energy, or thermal energy and then again convert it into electricity. So there are many pathways to utilize sunlight, and I guess we are inspired by nature. Um, but before we start, let me ask you this question. What do we get from the sun? What do we get from the sun? Mm-hmm. But what do we get? How how can the sun help sustaining life on Earth? Bong, what do we get from the sun?
Very photon.
Yeah, that's good one. Yeah, we get photons. UV, what do we get from the sun?
Heat and
Mm-hmm. But let's say we get energy from the sun, right? Do you think the energy we get, the energy that irradiated to the earth and the energy that released from the earth is equal out, or we store some in the earth? What do you think? You think we store some pasta?
uh, yeah, I think there's still some.
So if that's the case, then the earth would be hotter every day, don't you think? Right? The result, the answer is no. The in equal to out, basically. We get the energy from the sun, we use it, we convert it, and then we release it back, out of the atmosphere. But the problem nowadays, in is not really equal to out, because when we release the heat, it got trapped by the greenhouse gases, and then it reflects back to the earth. That's why the earth is warming up bit by bit. But if we talk about the past million years, the energy in equal to energy out. Okay, so the concept of entropy is a very important concept to understand before we go forward, right? The sun provides photons, right? Pong already said the sun provides very high energy photon. And typically, if one photon hit the earth, around 20 photons leave the earth, but lower energy photons. Basically, the sun provides a very low entropy energy, right, to the earth. Low disorder, very high energy density to the earth. But then our earth, we utilize those, we convert it into heat mostly, like IR. Our body irradiate heat, 36 degree. We use we run our body, for example, and then we release the heat back to the atmosphere, and that's the concept of how we convert the low entropy into high entropy, and that doesn't break the second law of thermodynamics, right? Because the second law of thermodynamics says what? We always go into more disordered, right? So if this image is true, meaning that the life on Earth is very good at converting high energy photons and into lower energy irradiation, right? So let's look at this. If we have a room like this and we want to make it cold, basically we want to decrease the entropy of this room to make it colder. It doesn't really follow the second law of thermodynamics because normally it can only get hotter and hotter, right? More disordered. But if we want to use air conditioning to keep this room cold, meaning that the entropy has to be released elsewhere. It can be released through transmission of electricity, or it can be released through burning of coal or fossil fuels to create that energy that we use to keep this room cold, right? So you can see that at the end we increase the entropy of the overall systems. It's not a magic how we keep the room cold. The plants also utilize this concept, right? So you have solar energy. The plant use the solar energy through photosystem 1, photosystem 2, release some heat, release some thermalized heat that we discussed last time, and grow, from this high energy photons. And then you can see this chain of reaction, right? The plant uses sunlight as the first creature, living thing to utilize the sunlight. And then we have the small animals eating the plants, and then eat those sugar, starch, and convert that into protein, to make sure that they sustain their functions, right? And then the bigger animal come and eat the smaller animals, and then we eat the bigger animal again. And all those things happening is the process of converting, solar energy into the energy we have in our body, for example. And then at the end, when we die, we release all those back to the atmosphere. That's why at the end, in equal to out. But living thing is very good at converting those energy. And we want to do that. We want to do that for converting solar light into fuels as well. Okay, so let's look at this and see why I'm quite interested in solar conversion, right? If you look at thermal engine like Carnot cycle, is never 100% conversion. You always have lost. If you study thermodynamics, from year 1, year 2, you will know that the efficiency of the Carnot engine is always below 100. The ideal case would be to have the hot part of the engine as hot as possible and the cold part as cold as possible so that you get the highest efficiencies. But there always be energy lost. But that's not the case in terms of photon conversion. Photon conversion into electron or into chemical energy, this theoretically can reach 100%. You can see the commercialized LED, for example. LED is very good at converting electrons into photons, right? LED is the opposite of solar cells. basically. Solar cell convert photon into electron, but LED convert electrons into photons. And the efficiency of LEDs, for example, red LED or green LED can reach like 90%, almost 100% already. So that's the key difference between thermal engine and then the photoelectrochemical process or photo conversion through semiconductor. That's the concept I would like you to understand. And if you have time, look more into it. Why the theoretical efficiency can reach 100%, why the Carnot engine can't. Of course, in reality, we never reach 100%. There is always resistance, overpotential, and many things, competing reactions. So it's very hard to reach 100%, but we can get very close. Okay, so the goal is to mimic, the goal of solar fuel synthesis is to mimic the photosynthesis. And another name of solar fuel synthesis is artificial photosynthesis, right? We want to mimic the photosynthesis. And what are the key components of photosynthesis? Pasta?
Two component,
Yes. What do we need?
carbon dioxide, and
Carbon dioxide, yes.
all plants is, we need water
Water
and we need light.
and light. Exactly. Right. So photosynthesis, we need carbon dioxide, we need water, we need light. Same as here, we need carbon dioxide, we need water, we need light. We're doing exact same thing as the plant are trying to do, but we want to make it in a more efficient way. That's why there are different systems here. And the goal of solar fuel synthesis is to convert photons into chemical energy. And that chemical energy has to have a high enthalpy, the energy within the bond compared to our starting material, carbon dioxide. And obviously, carbon dioxide is a low energy. We want to add more energy to carbon dioxide to create higher energy, higher enthalpy chemicals. Right? So for this class, I would like you to understand this basic concept. But I'm a bit old-fashioned, so if you can draw this, I will guide you through through this one by one and show you what are the key components and what are the important bits. So let me try to use my new gadget. Connect to the app. Why is it not connecting? Have to accept invitation. Why is it not working? Yeah, now it works. So let's see. Yeah. So you have the key component over here on your slide. So the way it works is you have the semiconductor. And then the semiconductor has the band gap, right? And you have the conduction band. And the valence band, right? When the solar light hit, it ejects the electron up to the conduction band, and then that electron leave the hole at the valence band, right? The electron then transported to the surface of the catalyst, and also the hole transported to the surface of the catalyst. And you have another thing called co-catalyst, right? You have the co-catalyst. The co-catalyst help to accept those electrons and then speed up the reaction, right? So you have this co-catalyst, and then that co-catalyst then help converting what? Let's say we make hydrogen, right? We convert photon into hydrogen, and then on the oxidation side, we convert H2O into O2 plus H plus. So, and the overall reaction would be H2O divided into H2 plus O2, right? So that's our overall reaction. The key for this is, so for example, the catalyst, there is the name for it, and we call it, for hydrogen evolution, we call it HER, hydrogen evolution, HEC, hydrogen evolution catalyst. And then for the oxygen evolution, we call it OEC, oxygen evolution catalyst. So the concept is pretty simple, but there is another requirement that ทันไหม? There is another requirement that I like you to see is the band alignment. So, for example, if you want to do water splitting, so this is the energy for water splitting, right? So you have the hydrogen evolution energy, and then the oxygen evolution energy. And that energy here on the scale is 0, and here on the scale is 1.23, right? So the catalyst that can perform this water splitting reaction, you can imagine that the catalyst band gap has to be overlapping like this. So the conduction band need to be above the hydrogen evolution potential. And then the oxidation, the valence band has to be more positive or below the oxidation potential to make oxygen. So in reality, the semiconductor needs to do this kind of thing in order to create enough energy electrons, transport it to the surface with the HEC, right? And then perform the hydrogen evolution. Similarly, hole need to transport to the surface, and the energy has to be a little bit more than 1.23, right, to create oxygen. So that's the challenge, because not only you have to consider the band gap, but also you need to consider the band position, the alignment, the chemical potentials, right? If you have catalyst that has the band gap of, has a large band gap, but the potential is not aligned, right? Meaning that you cannot make hydrogen here, but of course you can make oxygen, but the half reaction wouldn't work without hydrogen being produced, because the electron needs to go somewhere in order to create the whole, right? So the two has to happen simultaneously, otherwise the reaction will not happen, will not go forward. And so here I introduce the concept of this semiconductor. So this is called semiconductor or light absorber. Light absorber. And the band gap is this distance between conduction band and valence band. So that's the band gap, right? And then the co-catalyst, I already mentioned, right? You have different co-catalysts for different reactions. For hydrogen evolution, I wrote it here wrong, but HEC or OEC, yeah. Or you also have catalyst for carbon dioxide reduction. And redox potential is this line that show the reaction that we want to achieve. Another thing that happened within the surface of the catalyst is we have the electron going up and then the hole form, but it come back down, right? So that's also can happen. So if this electron doesn't rapidly transfer to the surface and perform reaction, right? It would come down. It doesn't want to be in the excited stage. So it would come down, meaning that to be able to develop the high efficiency catalyst, you need really good co-catalyst to help accepting electrons and perform chemical reactions that we want to achieve. If this catalyst is not accepting electron very well, or if this catalyst is not accepting holes very well, there will be a lot of back reaction, or I would say recombination. There would be a lot of recombination. So this is one thing that can happen, recombination. Another thing that can happen is back reaction. So the reaction we're talking about is always reversible reaction, right? So you produce oxygen and photon, and the other side you reduce photon and make hydrogen. The backward reaction also can happen. Right. The backward reaction also can happen, and that would reduce the efficiencies. So it's also important to find a co-catalyst that, promote the one way or one directional reaction, rather than, having it, you put so much energy to split water and then it just combine back then again. Another thing that can happen is for example, if you produce a lot of products, like you produce hydrogen can also be oxidized back, right? Or oxygen can also be reduced. So yeah, different thing can happen. So if you create a product, it's also important to take it out of this surface because this is an active surface. Different thing can happen. So if you make the good thing if we make hydrogen, oxygen, it's a gas phase, so it just bubble out, so it doesn't come back to be reduced or to go back to the previous stage. It's the same principle as a fuel cell, right? Fuel cell is the backward reaction of this. You have hydrogen, you have oxygen, and then you combine it, and then you make water and electricity. So the same thing can also happen here. Okay. So far, so good. Clear? I want you to be able to draw this kind of chart because it's a really important concept. Okay, now you have all the main components of the systems, right? You know that the light absorbers is the semiconductor that can absorb light, and then the importance of the band positioning, right? And then the band gap is also important. If you have the semiconductor like silicon with a very small band gap, nothing will happen. It just create electrons. That's why you use it for the solar cell, because you don't need to do any chemical reaction. You just need to extract the electron. That's why for solar cell we use silicon, very small band gap. Okay, and this is how the scientists in this field like to think about different materials, right? So you look at all this material and then you see the band alignment, and first of all you see the band gap, right? If it's so large like this, it would absorb very large, very high energy photons, and it wouldn't be efficient. If it's small like this, like silicon in your solar cells, it would absorb a lot of photons, but it wouldn't do any chemical reaction, right? But if you have the material like this two are very good material for water splitting. It can make hydrogen, it can make oxygen, but still the band gap is 3.2 electron volt, and that's can only absorb UV light. So we also don't want that. We want to make the ideal case would be maybe to have this material, but the valence band being located here, and then the band gap is only like 2 electron volt, for example, to be able to absorb most of the light. And this make it, because of this like requirements, the key difference between this and solar cell is that solar cell, we don't care about the band positioning. We just care about different layers to extract electron and holes out of your material as fast as possible. But here we care about the potential because we want to get the chemical energy out of it. So that's the key difference. And because of that, if you have time, go look at this Professor Andy Cooper. I will show you briefly here if it's working. So in his lab, he developed different kind of semiconductor for water splitting or for CO2 reduction to make the artificial photosynthesis system. But the student in the lab is way too slow, so he create a robotics machine that work 24/7.
liquids and you run it. And
So
then
he make like a different kind of library of materials, and then put some assumption that this material plus this material could make new materials.
Time.
He key that input into the
Optimize.
computer, and then the
we
robot
assess
just work
black
on its own and create
on
different data,
baseline
right?
activity before we did the
So it just
optimization. Ran that
measure under
check
sunlight, take the
stability.
hydrogen, and check the activities, and then do all this
You can
mapping.
see after 8 days, it gets
And
to
that can
accumulate
all be done
back to its-
autonomously
the components
without any
which
students.
is 6
So
times
this is-
more active than the.
This is one way the
dye
scientists try to
starts an
tackle
activity.
the
And
difficult
actually,
problem of designing the
dyes are
catalyst. We just do a
deoptimizer,
bunch and then pick the
So
best
is
one.
so are the surfactants.
And now he
the
incorporate
solids
also
going
generative
into
AI
the-
to make
The way it
the
works is
decision
not
making
actually
more
not neither negative nor
precise.
positive.
Because
But
normally
because
if you ask the robot to
not
do,
negative
you add
positive as
parameter
I
A
think it is.
and B, you create a bunch of data. But you need
And I
human
have
to
to
analyze
say,
those data.
Quick-
But now he integrated
quite interesting.
ChatGPT or generative AI to help analyze those data in real time. So once the data is generated,
And then
the
for about
AI
150
help
experiments,
analyze
we found any
and
base.
narrow
And
down
then it comes
the
back
next
to it later,
step of
having
the
removed none
of the
other
experiment.
components. So you can sort of see.
Okay, so that's very fascinating, and that's one way we can tackle this problem of material development because, when I started my PhD, we already talk about all this material. 5 years, 6 years past, not many material are being discovered because it's very hard to find a suitable material for, doing these difficult reactions. Okay. So there is another way that we can tackle the limitation of the band alignment. So I would like you to look at this chart. So at first we talk about single light absorber, meaning that we have one light absorber in our system. So we are really obliged to find a catalyst that fit all those requirements. But if we split the light absorbing into two parts, like photosynthesis, where you have chlorophyll, photosystem 1, photosystem 2 working together. So this is exactly that. So instead of having one materials that fit all the requirement, you can have two materials, right? One fit the first requirement and another one fit the second requirement, and the two materials connect and communicate, transport the electron between the two. Meaning that now you can have more variety of the catalysts that you can use. Not narrow band gap mean you can absorb more light, and then the potential that is way above. For example, this is hydrogen evolution. This is CO2 reduction to carbon monoxide. You can see the potential. So if the further we go from this potential, the easier the reaction can happen because we have over potential, right? So in this kind of design, now you can see that we can use two material working together to achieve the same thing, but with more, we can utilize more portion of the solar light from the smaller band gap of each materials. And this C scheme doesn't only apply with the particle system, but also you can do the same thing with the photoelectrochemical cells. So you have photoanode, photocathode, right? And one is the larger band gap, like this one, larger band gap absorbing the higher energy sunlight. And then you have the back electrode, photoelectrode, that has a smaller band gap that absorb the rest of the light. So in this case, it absorbs blue light and a bit of green light, but the rest just pass through to the second electrode, the C scheme. It's a very similar thing. And the second electrode absorb the rest of the light and help to run different reactions to complete the redox cycle. So that's the concept of the C scheme. Before we go further, I would like to point you to this chart. So if you look at the band gap, right, band gap of the materials, and you calculate the band gap into the wavelength of the solar spectrum. So 1 electron volt equal to around 100,200 nanometers, meaning that if you have the band gap of 1 electron volt like silicon can absorb anything from 200 to 1200 electron volts. So most of the energy, in the spectrum can be absorbed. This is the energy from the sunlight, right? So if you have silicon, which has a band gap of about 1.1, you can absorb this big chunk, this portion. But if you go back to the material that I mentioned before, like strontium titanate, right? 3.2 electron volts. And you go back to here, 3.2 electron volts here, right? If you stipulate that line down here, strontium titanate, it can only absorb the UV portion of the solar light because of the large band gap. But it's very good at making hydrogen. But at most, the efficiency here, they report 0.65 solar to hydrogen conversion. But even if we make it very efficient, it can, at most, it will go to 5% because that's the whole solar that they can absorb, right? So the scientists, what can they do? So they can form this kind of C scheme, two materials connect to each other, right? Like this case, bismuth monadate plus strontium titanate, like a C scheme system. Now it can absorb more light, but the efficiency only go up by a little bit, right? Or you can maybe go really easy way to use perovskite solar cells, connect with electrochemical cells, and perovskite solar cell can convert, has an efficiency of like 30%, and then connect with the very efficient electrocatalysis, you can get the efficiency up to like 12 or something. But yeah, you can see that regardless, most of the system that been reported so far only utilize half of the solar spectrum, right? So you see here, anything beyond 1300 is not being used. And this portion is infrared, right? The heat. Basically, the heat just normally thrown away by most of these solar conversion systems, right? So I leave the question in this slide, is the whole solar spectrum utilization possible? Maybe not. Because even plants that does very well in utilizing solar energy can only utilize this much portion, right? It can only absorb the solar, it can only absorb red light, it doesn't go beyond that. But the IR, the heat, give other function to the plants, right? It gives the plant warmer, for example, or the really deep UV region, it help the plant it give a little bit of stress to the plant. And then the plant, once they are exposed to those stress, they produce more vitamin, for example, or some plant, when they exposed to stress, they make purple leaf, which is what do you call it? Is it a carotenoid or something that is good for your body, like when you eat the purple salad, for example? So yeah, the plant absorb certain few portion of the solar light to function, but other portion of the solar light also help them grow or to help them thrive. And many researchers is now looking into this because, if you look at indoor farming, anybody here interested in indoor farming? Indoor farming, we always use the red light because we said, oh, chlorophyll absorb red light, right? But we don't look at other light, and we want to we want to use only red light because we said if you give them white light, the whole spectrum, the plant doesn't use it anyway. Why don't just give them red light? But it turns out that using white light can sometimes be more efficient. The plant grow taller, the plant grow bigger leaf, for example, create more vitamins. So this is something that, it's not just that straightforward things. that we said, okay, let's grow plant under red light, let's go wheat under red light, and then it produce the best product. But in reality, for example, for wheat, if you grow wheat and you want to get the CBD or THC from the wheat, you need UV as well to help activate, the formation, the synthesis of these different chemicals. Similar to our thing that we will talk towards, this lecture is all about combination of different things to make the most out of your solar irradiation. Okay, now I leave you with these questions. So if the light absorber has a band gap of 2 electron volt, how many % of the solar light can it utilize? You can go back to the previous chart and draw some line and answer me. Okay, how many percent? 2.1. 2.1 electron volt. Look at this line, the dot line. I plot this energy from this solar spectrum. I plot this energy content, right? How many percent? 15? I don't know. 2? Yeah. You see, with the catalyst that is 2.0 electron volt, it absorbs. At most, you can get the efficiency of about 20% out of this system. In reality, it's lower because of what? Because of this, right? You have to have a little bit more energy, and you have to have a little bit more negative, more positive potential also. So you always go a bit extra. And if you look at the catalyst, the best catalyst like this one, strontium titanate, this is the world record of the catalyst for water splitting. You can see that for hydrogen, a little bit extra is enough because hydrogen is rather easy. But for oxygen evolution, you need much more oxidative valence band to be able to make oxygen. So that's one of the key problems in the catalyst development. You want to increase the light absorption, but then by narrowing the band gap, but you also lose the chemical potential for making energy. So that's the dilemma between the catalyst design and what you can get out of it. Okay, so this is key parameters for this field. One is production rate. production rate tell you how much hydrogen or CO2 reduction products is produced over the certain amount of time. And that's straightforward. The solar to hydrogen is the key metrics, or solar to fuels. So solar to fuel is the big umbrella, and then solar to hydrogen is the subset of that solar to fuels. So it's about how much energy you can convert from the solar energy, right? And then you have the EQE, which is the external quantum efficiencies, and then you have Faraday efficiency. So let's go one by one. So this is a basic formula of solar fuels. Solar to fuels is basically you take the energy output of the chemical energy output of the product you created, and then you divide it by the total amount of light you shine into the materials. And so this is the way to calculate it, right? So you have let's say you have hydrogen. So hydrogen, you add the production rate first. How much hydrogen in the unit of millimole hydrogen per second, and then you times that by delta G, the energy requirement for producing that hydrogen. So as I mentioned, the thermodynamic requirement for produce hydrogen at standard condition is 237 kilojoules per mole. So you can put that number here. Make sure you look at the unit properly. And then you divide it by the solar irradiation. And normally there is a standard, one sun standard. This is about 100 milliwatt per square centimeters. And then you times that by the area of your device. And if you input all this, you will be able to get the solar to hydrogen efficiencies. And I will give more example. I think in the next class where we will try to calculate this, but right now just grasp the concept. Very simple one. So the next one is the external quantum efficiencies, and this is a very important concept. It explains how much the number of electron that is usable in the chemical process divided by the number of photon that you put into the surface, into the material. So imagine, just go back to the picture that I asked you to draw. So if you put 100 photons and it creates 100 electrons then to be used, then that EQE is 100%. But in reality, the EQE is maybe 20 to 30% because of the recombination and also other things. So this is another metrics that people, when they develop a new catalyst, they try to improve the EQE so that the number of photon that they put in will equal to the number of electron that perform different reactions. So that's another thing, right? And another thing here is Faraday efficiencies. Hide the video. Hi. Okay, Faraday efficiencies. This is another metrics that tell. So from the EQE, you know how many electrons you get, from injecting the photon, how many electrons got separated, and help you run reaction. But Faraday efficiency tell you out of those electrons, how many goes to make different products, right? So if you have 100% electrons, in this case, this catalyst, they make mostly hydrogen. So you can see here, 70% is hydrogen. The product, this is to tell the product distribution, right? So out of that 100 electrons, not 70 made hydrogen, right? And then about 10 make alcohol, right? C2, C3 alcohol. So this Faraday efficiency will tell you essentially the product distribution. And when you run any reactions, you want to account for all those Faraday efficiencies. Because if you only measure hydrogen and then you say, oh, it's 80%, you don't know what that 20% electron is doing. So when normally when you run the reaction, you always want to know where does the electron goes. It can go back to the system or it can perform and make different kind of product. In this case, making alcohol or carbon monoxide, for example. And if you combine this all, it should make up to about 100%. It should be a little bit below 100%. Right. Okay, so this is the thing I want you to look at. So I have two catalysts, right? Now we look at the EQE, meaning that the ability of the material to generate the usable electrons, right? If you have the first material, can only absorb up to 380, only UV light, but it's very good. It doesn't have much recombination. Whatever electron produced can be used in the reaction. So the EQE is about 100%, right? But it can only absorb until it only absorb until 380. But the second materials is not really good at separating electrons. You have a lot of recombination. So if you measure the EQE, it's about 40%. But the second material absorbs more light. It has a smaller band gap, absorb more light. Which one is better? Right. So this is something that people don't talk about often. When we talk about photocatalysts, we always want to say, oh, we want to make sure that the electrons, we absorb more electrons. But in reality, it also has to do with the efficiencies of the conversion. So the way you do this is you have to calculate the area of the graph, right? So in this case, maybe both are about the same. Maybe A is a little bit better, but B absorb more light. So yeah, it's So I want to show here that there are two ways of development. One is to make sure that you absorb more light, and another one is to make sure that your material is very efficient in making those usable electrons to do different reactions. And that's the project that Pasta and Gam will be working on. Yeah. Okay. What time is it now? So this class finish at what time normally?
12.
11:30.
11:30.
Okay. Anyway, I want you to look at this concept that when you want to compare the two catalyst systems, activity is not everything, right? So if you have the system A suspended in the solution, right? And then you shine the light, and then you calculate the production divided by grams of the catalyst. And then you compare with the system B from another researchers using the same condition. You say your system is better, but it definitely is a different catalyst, right? It's not fair. Normally, what you do as a researcher is that you have the system A, and then you put the powder inside the solution and optimize until it reach the plateau of the activities. So like this one, right? So you have system A, normally when you increase the amount of the catalyst, the activity increase and then it plateau, right? And then system B is the same thing. You optimize and then it plateau. So the way you compare the two systems, normally you compare at the peak point, the plateau point of the system. You can't just take the number here and say, oh, the two material at 2 milligram per at certain condition, one is better than another, because at this condition maybe A is better, but in reality at the optimized condition B is better. Similarly for electrochemical cells, when you make electrodes, right? Sometimes one system can be scaled up better than other, right? For example, system A very efficient in the small size, right? But once you scale it up, system A lose the activities drastically, but system B can scale very nicely and only lose a bit of activities. So these are the two main things that if you go into this kind of research, you have to, or you read the paper, you need to be cautious of whether they compare at, their maximum potential or they compare at certain condition and you just say, okay, A is better than B, even though B is actually better than A. So that's one thing. Another one, I won't talk into it, I won't go into it, but I want to show this is the different colors of hydrogen. Have you heard green hydrogen, blue hydrogen, gray hydrogen? As I mentioned in the first class, hydrogen is very useful because it can upgrade your CO2 essentially. If you have carbon monoxide and hydrogen, through the Fischer-Tropsch process, you can make any molecules in the world, right? So it's very important to find a green hydrogen to react with your carbon source so then you get the green chemicals. But normally now you can see here green hydrogen or renewable hydrogen only account for a very small portion. And most of the time, when you go into the decarbonization or when you go into work in a company, you will see all these different kind of hydrogen. And this is really useful. It's not bad hydrogen. Any hydrogen is good because you need to slowly transition from the non-renewable to renewable. And one of the easiest way to do that is to put hydrogen into, for example, into gas pipe, into natural gas pipe, right? And instead of burning 100% natural gas, you can burn 80% natural gas and 20% green hydrogen, and that reduce the carbon dioxide emission of your electricity already, right? So we all need this. It's like chicken and egg. You need infrastructure to start to build up until you can utilize hydrogen or until you can achieve, hydrogen economy. Just to show you how the different colors look. Okay, I think we should take a break here, maybe 10 minutes break, and then we will be continuing our lecture at 11 for another half an hour, and then we will leave at 11:30. ไม่มีขนมจากอินเดียพากาแล้วก็อันนี้ขนมจากwhere is it ออสเตรียno ออสโลประเทศอะไรวะฟินแลนด์นอร์เวย์ เคเดี๋ยวจะไปเร็วแล้วนะ อธิบายคอนเซปต์ยากๆเสร็จแล้ว อร่อยไหมอันเนี้ยอร่อยนะ ผมก็ยังไม่ได้ลองเลย โอเค next we have this อ้าวตื่นละเมื่อกี้ง่วงมาก Okay, next we have this chart called this is the product that normally you get from this process that I explained before. So you get hydrogen from water splitting, you get carbon monoxide from CO2 reduction. Sometimes you get formic acid, you get methane, methanol, ethane, ethylene, acetic acid, ethanol. So you see that all these molecules are the smaller molecules that you can get. And as I mentioned last time, our goal is to connect this and make the larger molecule. But this is a very good way to think of how we can utilize the carbon dioxide, which is the greenhouse gas, into useful chemicals that then we can convert into something even more useful, right? And this is the energy that required for this process. You can see that the easiest one would be to make hydrogen. But if you want to make carbon monoxide, a bit more useful chemical from CO2, it requires a bit more energy. And if you want to make ethane, right, it's really requires so much energy here. And another thing that you have to note is not only the chemical potential that the molecules need for the reaction to happen, but also you have to look at how difficult the kinetics of the reaction. So if you talk about hydrogen evolution, it's a 2-electron process. You need only 2 electrons combined with the photon, and then you make 1 hydrogen. But if you want to make ethane, for example, it's a 14 electrons process, right? You need to combine CO2 with 14 electrons in order to make ethane out of it. So that's even more challenging. And if you talk about artificial photosynthesis and making hydrogen is the easiest one, and you only get one product. But if you talk about CO2 reduction, sometimes you get carbon monoxide, sometimes you get the mixture of carbon monoxide and hydrogen because the two reactions are competing. Or sometimes you get all this mixture of product. And the thing is, if you get many kind of product, that it will be a challenging separation process along the line, right? So that's what we're gonna talk in the next class. Which one of these has the highest potential in terms of like economics and the market demand and so on. So that's also important to note. So now I will go through mostly the current research on how what kind of strategies people use to improve the solar fuel synthesis. Through one is like improving absorption that I mentioned before. This one I would not go to. It's about engineering the materials, making the band gap align the band gap that I have already mentioned. Another thing is light management. So this is a very interesting area for people to go into now. As I mentioned, one catalyst cannot use the whole solar spectrum. So can you manage those light and make it more useful? Another thing is to develop the different co-catalysts to make it, as I mentioned, to reduce the back reaction, to promote the forward reaction, to increase the EQE of your system. So that's also another area that people work. Okay, the first concept I would like to show here is the light management. This is mostly theoretical, but I would like you to understand the concept. So if you have, in the first case, if you have a really high energy photons, right? And this is your materials. Your material is only the band gap of your material is only this much, but you have a very high energy photons. You have a very high energy photon, meaning that many of this will be lost in the form of thermal, right? As Professor Paravi has mentioned, the thermalization loss. You have very high energy photon. It needs to relax down to the conduction band to be able to perform different reaction. So in this case, you can have something called the Dow converter. Dow converter is the coating materials that would convert your UV light high energy photon into two smaller photons. So instead of having one photon and then most of it lost in the form of heat, you split that photon into two different lower energy photons and use both in your catalysis. So that's also a strategy of using the Dow converter. That's materials, right? Another one is the Dow shifter. Dow shifter is also similar concept. You have, but this one only create one photon. So it doesn't make much sense really. But you have the higher energy photon, but the Dow shifter modulate the photon energy to match your catalyst. So then your catalyst become more efficient and less heating on the material, on the catalyst itself. So that's also Dow shifter. And yeah, there are many other things. For example, this is the triplet annihilation up converter. Up converter is meaning that you have a small energy photons like the IR, the infrared, and then you combine those IR and make it larger photon for your catalyst. So that's like in this case, you can see you have the IR and then you increase the energy by combining 2 or 3 photons in the near IR region, and then you make, for example, UV to activate your catalyst. So that's are the 3 main system that I like to talk. These 2 are quite similar. So what you only have to remember is if you have a large energy photon, you can split it into 2 lower energy photons. If you have large energy photon, you can modulate it and make the suitable photon for your catalyst. Or if you have lower energy photons, sometimes the material can up convert, make a high energy photon out of that smaller energy photons. So that's light adaptation, right? So you adapt the light to fit your system. That's one strategy. Another strategy is beam splitting. As I mentioned, maybe your system is only good with UV light. So why don't we just split the beam? So you have the crystal and you have the light coming in and then split into UV, into visible, and into thermal, the IR, right? And that meaning that you can put your system one here, and then the rest of the light, maybe this can go to photovoltaics because photovoltaic is good at visible light, and the IR can be used for different thermal systems. So you have the light and it's split and use it for different applications. So that's also one way to utilize the light better. Another one is called light trapping. Light trapping meaning that normally when you have the photon coming in, some of them get absorbed, some of them get transmitted. It's really hard to find, to match the material, your material thickness and everything with to absorb all the light from your incident light. So this light trapping strategy is to reflect the light back. So for example, if you have the anode material here, the photocatalyst here, it absorbs light. Some of them pass through. This material can be tuned to reflect the usable light of this photoanode material back another time. So it creates a double pathway. So not just going through one time, but go through and then like a mirror go back again. So then it use most of the photons that it can use. And then this material can also transmit another certain photon that this material cannot use anyway to the second absorber on the back. So this can be the smaller bandgap absorber. So this is light trapping strategy. So I introduce here 3 strategy. One is adaptation, another one is splitting, and the last one is trapping. Okay. Okay, here what I want to show here is the state-of-the-art system for photocatalyst. So as I mentioned, photocatalyst, normally when you run the experiment, you just dissolve it in water and then shine the light. But that is not really scalable, and if you want to increase the system scale is very hard because everything is in solution. It's hard to process, it's hard to release the gas, it's hard to recycle. But if you put the photocatalyst, fix the photocatalyst onto the substrate, right? You can make in this case they put it on the glass substrate. They can make big panel like this, right? And this big panel has been shown to run consistently over like past 2-3 years. And this is a demonstration in Japan. So you can see that the panel look like this with the white powder on top, and you have the water flow in and out. And then you have the separation unit somewhere here to separate hydrogen and oxygen that the panel create. And this is an example of when I said you have two options. You increase the absorption of your photocatalyst or you increase the EQE of your photocatalyst. This researcher, Professor Kasunari Domen, who been waiting to get Nobel Prize for the past 5 years. This year he missed it again, but hopefully soon he will get it. But yeah, this professor, he took that EQE route. So he chose this wide band gap material, but he tried to make it as efficient as possible in terms of the light utilization. So this material use almost 100% of the coming light in the UV region, meaning that the demonstration here, he can get the solar to hydrogen of about 0.65, actually about 1%. 1% solar to hydrogen, and theoretical number would be about 5%. As I mentioned, the UV portion is about 5%, but you can see he already get a lot out of the UV region. And as you can see here, we will talk further into our next class. Is you can see here that if you want to manage the light, you see here the material only absorb UV light and a lot of light still pass through. So one would think that maybe if you introduce this kind of solar farm, right, you may be able to grow some plant underneath because plant use visible light, right? So that's to help reducing the land use competition between energy harvesting and food production. And that's the two areas is always competing for space. And the way he increased the EQE here is he designed a co-catalyst. You can see here. The co-catalyst that is one directional, right? So he has the co-catalyst deposit on one face, one crystal face of his material, drawing all the electrons. And then he has another co-catalyst deposit on another face of his material, drawing all the holes. So everything is always separated into to do different reaction, to do their respective reactions. And that this strategy that he introduced, rather than randomly deposit co-catalyst around your material, this strategy improved his EQE from, it used to be for the same material, it used to be 60-70%. Now he make it 100%. So that's why this paper got accepted into Nature. Okay, I already mentioned about the C scheme. So you can see here that another way, apart from increasing the EQE, AQY is similar to EQE. You can think of it as EQE, it's okay. You can see here that there are two materials absorbing. If you talk about this material, right, it absorbs only until 360, 380. But this material, you can see the two materials, A and B, absorb more light, and this material can absorb up to like 500. But the EQE is less. The EQE is not 100%. The EQE is 20%, right? 15%. So this is also another strategy to increase the light absorption. But this system that use these two materials also give about the same efficiency of about 1.1% solar to hydrogen, and this is currently the world record. And Pasta and Gam, we are trying to break this record through his senior project. So yeah, That's a big goal, but this record has been set since 2016. And hopefully this year we can break the record and make 5%. Yeah. Okay, so this is the work done by my friends at Nagoya University. She's now Professor Qian Wang. I'm also inviting her to be adjunct professor in our department. So maybe early next year, you can hear her lecture. So she developed the process to scale up this system of C-scheme system. What she does is she has like these two particles. So the C-scheme consists of two kind of particle. One is for oxygen evolution and one is for hydrogen evolution. And it's connect electronically by mediator. In here, what she did is she developed a particle transfer methods. So I would like to show you this is the work in 2016, right? The world record. So this is how she achieved it. She has a glass plate. She drop cast her OEP and HEP together onto the glass plate. And then the two particles is still not communicating. You need something conductive to make the two particles connect and communicate. So she deposit gold layer on top. And then after that, she put the tape on top of the gold layer and then peel off the material. So that's why it's called particle transfer. So she put the tape on top here and then peel off. And then from this layer, only the top layer stick, back to the back. So you have the two kind of particles connected by gold layers. And then with the carbon tape that you use as the tape to take everything out. And then with the glass underneath. And using this, she achieved the world record of 1.1 solar to hydrogen. And then later work, they developed some kind of ink. So instead of using gold, which is very expensive, they make like the conductive indium thin oxide, which is the conductive nanoparticles, and you mix everything in the ink form, and then you just spread it out. You just do the screen printing, and then you make this kind of materials, this kind of photocatalyst sheet, and achieve the similar efficiencies. So that's the development from the first work. And this work I'm also involved in this is, as I mentioned, it's not just about the material here. It's not just about the light absorber, but it's also about the catalyst. It's about a co-catalyst, right? If you want to do interesting reaction, you need really selective catalyst. And what can be more selective than living things like bacteria? So here we put bacteria on top of our photocatalyst sheet. Bacteria, what does bacteria do? Bacteria normally they eat formate. Is this formate or acetate? 1 second. Acetic acid, yeah. Normally this kind of bacteria. So look at this part. Normally, forget all the arrow. Normally bacteria eat acetic acid and then they grow and then they release carbon dioxide, the opposite arrow, and then they inject electron, onto something. So that's how the living mechanism digests food, right? We digest the energy containing molecules, we release carbon dioxide, and then we have the electrons that needs to be transported somewhere. But in here we do the opposite direction. So we inject electrons and hydrogen into bacteria directly and then force it to do backward reaction. So instead of utilizing eating acetic acid and form carbon dioxide, we inject the electron and then we force the bacteria to use carbon dioxide and make acetic acid. Right? And this bacteria, if you talk about catalyst, for making acetic acid, normally the Faraday efficiencies that we mentioned is like 60-70%, very, and most of the thing go to hydrogen, for example. But in the case of living organisms like this, we can get 98-99% from acetic acid out of this hybrid system. So you can see the importance of choosing the right catalyst as well, to use with the system that you have developed. Okay, the next one I would like to talk is photoelectrochemical cells. So this is another approach, right? You have the first approach where you have the catalyst, powder catalyst. You can either use it in the suspension in water, or you can stick it onto the glass. But this one you try to separate the process. So you separate the reduction and oxidation. Reduction happening on photocathode and oxidation happening on photoanode. And when you have this two separation of the light absorber, you can have the product separation. So not just the powder making everything in one powder, but now you have two separate compartments, and these are the different configurations, right? You can have photoanode, photocathode separated by membranes that transport. This is called photon exchange membrane. So you have, one side you produce this photon, and then photon transport through the membrane to be reduced and make hydrogen to complete the cycle. And from this concept, you can sometimes do it back to back to make a device that is more compact without any membrane. So this is called artificial leaf. So you have photocathode on one side, photoanode on one side, and then run to produce your reaction that you want. And put the focus on the light. You see, for example, this part, you always have the larger band gap in front to absorb the higher energy photon, and the lower energy photon go through to the second absorber, because in reality you don't get the solar from two sides, you only get from one side, right? So normally this is how we design it. Or even this case, normally we just shine the light from one side and then pass through to the second side. So this is the C scheme, right? You have two absorber connecting. This can be seen as C scheme. This is a single absorber. So you have light absorber, and then you have dark electrode to do the same thing. But in this case, you need both electrodes to work together to run the overall reaction. But in this case, your material can sometimes be already good at making, in this case, has enough energy to drive hydrogen evolution as well as oxygen evolution. So the material, if it's a photoanode, it can produce oxygen on its own, and then the electron is transferred to another chamber through the dark electrode. This can be platinum, nickel, the thing that doesn't absorb light, and then that high energy electron, enough electron with enough energy can reduce that proton into hydrogen. H2 is proton, we call it proton, right, into hydrogen. Or the opposite can apply. If you have a strong enough photocathode, it can produce hydrogen, and then the electron, the hole, go to another side and produce oxygen. So these are the different configuration of the PEC or PEC. The important things here is this chart, right? When you have the photoanode and photocathode, normally, I think Professor Paravi has taught you about this, the LSV scan of the solar cells. Have you seen this kind of chart? The power, the IV curve of the solar cells. Yeah, very similar. So when you have photoanode and photocathode, you have the IV curve of the two materials, the two C scheme material. And normally what you do is you overlap that IV curve, and whatever the point that it overlaps, that's the current. This is the current. This is the performance of the material of your overall device that you can get. So it works at this matching current, matching curve, right? And so that's one thing. So if you have two materials, you run LSV, you run IV curve separately between the two materials. You plot and then you get the overlapping part. That's the current you can get. Another thing that is important is that the point at which the two curve intercept, that voltage is the voltage that your catalyst feel, right? So in this case, the two overlap at about 0.5 volt, meaning that your anode will feel 0.5 volt, and then your cathode will feel minus 0.5 volt. That's how the catalyst feel, and that I mean by the catalyst feeling that potential, meaning that's the potential that will perform the chemical reaction that you want to perform. So if you go back here, right, you see this is how different catalysts perform at different voltage, right? If it feels on the catalyst of minus 0.7, it produces a lot of hydrogen. But if it feels less negative potential onto itself, it produces less hydrogen and more alcohol, right? If you run at lower than that, it produces even less hydrogen and more alcohol, like 20% alcohol. So that's important, right? So if you want to talk about your device performance, you need to understand the overlapping and also the position it overlaps, right? Because this is how much voltage, how much potential your catalyst feel, and it will perform the reaction accordingly. And in ideal case, if you want to make the best device, you want the current to look like this, the IV curve to look like this, and it overlap at very maximum point, so that you get the best performance out of your photocathode and photoanode. But in reality, it never like that, right? This is the example of the device my friend made. So what I want you to see here, this is the photocathode part, right? So normally when you do the overlap, you flip this chart up and you overlap with the photoanode, right? But in this case, you can see here, without the co-catalyst, without a good co-catalyst, you see the blue line. If you flip the blue line up and overlap with this and try to overlap with this, it has a really small overlapping. But once you add the suitable catalyst on top, it makes it even more current, more like prettier curve, right? So what you want to do is you want to make your curve a little bit, better to increase the overlap, right? You need to make it either go this way or go this way. That's the onset potential of the IV curve. That's the VOC, right? And also you want to increase the current to the top. So here you can see here the VOC is the same, but the current go up. Same here. This is without the catalyst, the blue one, and once you put the catalyst, the current goes up, right? And when you overlap these two systems now, it can work under bias-free condition, meaning that you have two light absorber connect, and then it will perform the reaction that you want. I would like to point here that one of the most notable catalysts or co-catalysts to be put on your system is copper. Copper has a very interesting property. It form bonding with CO2, right? It activates your CO2, but it form very weak bond with the CO. So normally it take your CO2, it reduce, it give the energy, it give the electron to CO2, CO2 becomes CO. And then what copper does is they couple that CO, that that stick onto the surface, and then they kind of combine it and create longer bond. So that's the copper property. But if you talk about other material like platinum or other metal, it might form too strong bond, meaning that once the carbon dioxide hit the bonding of the material, it just stick there and it doesn't perform anything. So copper has been used in many CO2 reduction system, especially for making alcohol, for making longer molecules. So we talk about C1 is carbon dioxide and carbon monoxide, right? You make C1 product is carbon monoxide. You can make C2 product like ethanol, right? You can make C3 product like propanol or other alcohols. So with the copper, you see here, this is Faraday efficiencies, as I mentioned. You can see here that at certain voltage, it produces hydrogen, ethane, ethylene, all those things. And you can control this product distribution by varying the voltage that apply or the voltage that the catalyst feel, right? So if you look at this and you said, oh, the catalyst feel about 0.5. If you have the two system like this and you expect the catalyst to feel the bias about 0.5, you can go back to this and you can go, oh, okay, 0.5 here. Your co-catalyst is producing a lot of hydrogen and CO at this potential. So when you stick this catalyst onto your light absorber, like this co-catalyst onto your light absorber, it will mostly produce maybe syngas, hydrogen and carbon monoxide. There are different ways to make the copper more active and better. So in this case, we want to increase the surface area of the copper catalyst. And here, this is how we do it. We make a lot of hydrogen bubbles. We grow the dendritic copper onto the copper substrate using hydrogen bubble as a template. So when you apply negative potential, what you get is hydrogen bubbles, right? And once the bubble form, the copper is being deposited onto your material as well. And the bubble gets a bit bigger towards when it releases from the surface. So you ended up with this kind of foam like this with the small dendritic structure, and this increases the surface area and also in this case increase the alcohol formation. And this is what you will see here. So this material, again, Faraday efficiency for alcohol is about the best condition is about 15%. So it produced from CO2, it produced mostly hydrogen, and then about 15% is alcohol. Why is this important? Is that I want you to see here that regardless of the system, this is the copper alone, and this is the this technique combining copper and palladium and make it more efficient. You can see here that at the end it produces many kind of products from CO2. CO2 is very hard to make, to make single product like what the plant does, making sugar. In reality, if we want to do those things, we end up with multiple products, and the separation along the line is also a key factor in judging whether this process is viable or just useless. And this I already mentioned, we can not only we can use like copper or other like the inorganic co-catalyst, but we can also use living things as a catalyst. And as I mentioned already, the good thing about living thing is it can regenerate. So once it dies, you add a bit more nutrition, it regenerates, and it's also very selective. Like 100% you make single product if you use this kind of system. Rather than copper, you make 5 kind of products, and it's very hard to separate at the end. This is just a chart to show how you can grow the bacteria on the substrate. So this is very interesting way to make the substrate for bacteria to grow. Basically, you have the polymer beads like polystyrene, and then you have the ITO, indium thin oxide nanoparticle, which is the conductive nanoparticles. You mix them together, you deposit onto the glass substrate, and then you burn your polystyrene out, and then what you're left with is this inverse opal structure, ITO, and this is conductive, and the bacteria really love this kind of cavities and grow. So you can see here, if you take the image, you can see this small bacteria growing, and this bacteria is ready to work with to eat your electron and create different reactions. Okay, in terms of scaling the system, as I mentioned, there are two approaches now, and there are three approaches. One is photocatalyst, PC. Photocatalyst, the way you scale is you put it on the glass substrate, you put it on the substrate, and then you run it. It scales really well because it doesn't, the particle itself work as a separate engine, right? It doesn't have to connect with anything else. The material will work. So the performance of 1 square centimeter and 10 square centimeter will be the same because everything happens the same way. You produce hydrogen and you produce oxygen in a small scale and a large scale. But if you talk about PEC, where you have electrode A and electrode B, and you have to make the membrane in between and so on. There are many ways to scale it. And these are the example of the way you scale it. Like I mentioned, you can do back to back, making artificial leaf, but electron doesn't communicate very well in this configuration, right? You can have it side by side like this, photocathode and photoanode side by side, both absorbing light and then communicate through this small channel, right? So these are the way people try to increase the area, the size of this. But again, it's still ongoing process. So I just want to put here for you to look into in case you're interested. But right now, we still don't know what is the best. You can see there are many problems in terms of scaling this system because you have A and B, and the electron needs to communicate, meaning that you have the electrolyte, and then you also have to separate the product. You have carbon dioxide reduction product on one side, you have oxygen on one side, you don't want it to mix. So you have to either put it this way or put it back to back like this, or sometimes you put it this way like a staircase like this. There are still no single, what do you call, single solution that fit, all the system. Okay, I would like to show you, this is a part of my work where we try to use the full solar spectrum, right? So when we talk about IR, if you go back to that chart, this chart here, right? You see this dotted line. If you take the best example here, you can only use about 65% of the solar light. The rest is still not being used. And I asked you the question whether we can use the whole spectrum, and I said may be difficult, but could be possible. Like in this case where we try to capture the heat behind our photoelectrochemical cells and then feed it back to the system. This is how it works, right? So what I did is I create a cell that has a really small, tiny amount of electrolytes. So this is the two electrode facing front like this, right? You have a hydrogen evolution on this, and then you have oxygen evolution on this. And then what you want to achieve from this design is to make the front part heat up while the back part kept cool. Because what thermoelectrics does is it captures the heat difference between the cold and the hot. and then generate electricity. So this is the diagram of how it looks. So you have thermoelectrics trying to capture the heat difference between the hot part that heat up naturally by the sunlight and the cool part. I have put the water jacket on the back, right? This, 20-degree difference, the thermoelectric can capture and produce electron and feed back to my system. So everything is connected in series, right? Put it back to my system. So this is how it looks like when we did the prototyping. So we did some 3D printing cells and then we test, and then at the end we did some machine milling, CNC, and make like a proper device out of it. Okay, the important chart I want to show you is this one. So as I mentioned before, the overlapping part is the most important part that tell what is the performance of your system, right? And without the help of thermoelectrics, this is the overlapping part, right? The catalyst field about 0.5 volt on itself. But this doesn't matter because what I'm doing here is hydrogen evolution. So hydrogen evolution can happen anything below 0. Hydrogen evolution can happen. So we don't care so much about the position, but as you can see here, the position can be shifted. So if in the case of putting thermoelectrics here, you see that not only we get higher current out of our photoanode, so the yellow one is a photoanode connected with thermoelectrics, but also the shifting of the overlapping point here also will help in the future device where we want to do carbon dioxide reduction, for example. So as you can see here, I demonstrated two systems. One is the bismuth monadate and perovskite, so the two light absorber. And as you can see here, under one sun, because under one sun, like natural sunlight, not much improvement you can see, because normally the cell doesn't heat up too much. But once we start to concentrate the solar light onto our system, you can see the increase, and if you concentrate the solar light 5 times, you heat up the cell so much that thermoelectrics works even better, and now you can see the performance increase by like 2 times. And as I mentioned before, if you have photocathode and photoanode and you have the IV curve and it doesn't overlap like this, right? If it overlap, it works, but if it doesn't overlap, like in the case of this two material, perovskite and hematite, it doesn't really overlap. But when we introduce this concept, it kind of push and make sure that the two material overlaps. And this is also quite a smart strategy in order to make the two material that would never be able to work together now can function together. Okay, and we also did the same thing, but this time it's carbon dioxide reduction. So instead of using platinum to make hydrogen, we use enzyme. I mentioned living things is very good at converting carbon dioxide to one product. So this one we use formate dehydrogenase. So it would produce formate from carbon dioxide, right? So the question we want to answer here is whether we can get CO2 reduction on the single light absorber. So without using two light absorber, now we want to use just one, but one with the help of thermoelectrics, right? And the second one is, can we see the effect of the temperature? Because we know that once the temperature increase, and if we can control it well, we can increase the kinetics of your reactions. So this is what we set to do. And yeah, the system is about the same. And we show here that the enzyme works better at higher temperature. And our system can work with only one single electrode. So as you can see here, normally without any thermoelectrics, you don't see the overlap between the anode and the cathode. the cathode and the anode. But once you add thermoelectrics here, it push the current of the anode here, and then you can see now the nice overlap. Okay, and in terms of scalability, you will see that for the photocatalyst system like this, it scale up really easily. So as I mentioned, you have the powder that works on its own in a single powder form. So no matter how much you add, it will be able to scale. So in this case, we just cast our material onto bigger substrate. That's how we scale up, right? But in the case of photoelectrode like this, because as I mentioned, the electron needs to communicate to the other side, right? So in the case of bismuth monazite or photocathode or photoanode material, if you have a very small size like this, electron transport very short distance, no loss, right? But if you have a bigger substrate like this, electron that produced here, if you have the contact over here on top, the electron that produced here and the electron that produced here will suffer different, travel distance, right? So how people scale up is they make like this kind of like conductive comb like structure to help transport the electrons from one side to the other, right? So that's the engineering challenge in terms of like scaling up and trying to make it commercially available. That's difficult. Another way that is a little bit easier is to concentrate the light, right? If you have the device 10% efficiencies, right? If you want to get product from this device, to run your house, maybe you need this space, right, to absorb one sun irradiation. But if you concentrate it into 4 sun, right, 4 times the amount, your device, your absorption area can reduce. You take less space to get the same amount of energy. If you concentrate 100 times, you can even make your device even smaller. And normally the expensive thing is the material of your device, right? So there are many ways to concentrate the sunlight. But the thing I want to point out here is solar energy the sun always move, right? So if you want to concentrate the sunlight, normally your concentrator has to move with the sun. And that is very expensive to do, right? So people try to make concentrator, but it only works for certain angle of and certain hour of the day. But if you want to get the most out of the concentration, you need to have the adaptive concentrator that move with the sun. And that's what I draw here. So the solar concentrator needs to move, or your material or your device need to move to get the best amount of light coming to your sample. But the good thing about this is that you can scale up like this, right? You have this big space in desert, and then the sunlight coming in, you can have different mirror and concentrate your sunlight to one point and put your active material here, right? The mirror will be relatively cheaper than making the device the same size, but it concentrates all the light, and then you have the active material here. Another way to think of energy is to also to think about food, because the space is what we are fighting for, just like plants. Plants fight for space to grow, right? Smaller plants will suffer if they don't get enough light. If it got covered by the bigger plant, that's why it has the need to grow a bit higher to get the light. Similarly, if you want to get the most out of your light, you have the in nature you have the plant with the strong with the high requirement for solar energy, and then you have the shade plant that only need a bit of solar energy, and then you grow your product of the photosynthesis is biomass, right? So you grow the most amount of biomass out of that space by the nature creating the sun, the tree that use more light, the tree that use less light, and the tree that almost use no light, like moss or those things on the ground. And all those create biomass, and then you get a lot of biomass out of the same space. Similar idea here. If we talk about solar panel, right? And it utilizes only 10% of the solar light, or even 1%, the world record that I mentioned. You have a lot of sunlight being wasted. So there are many people, I mean, looking into this area where you want to grow food or things underneath the plants, underneath the solar panels or photocatalyst panels in order to maximize the land use. And I show you a picture here where this kind of panel can, transmit a lot of light, and this space can definitely be used for growing, shade plants like berries, strawberries, for example. Okay, the group project for this, how many people are there? 1, 2, 3, 4, 5, 6, and then one missing, 7. 7 or 8. If you don't count Thai, it's 3.
Okay.
8. Yeah, so I have 4 problems that I would like you to help me think. One is, one of my friend worked for the company that produced mango to be sold in 7-Eleven, and from the peeling of the mango and from all the waste, and also they sell salad to 7-Eleven, and his company create about 10 tons of waste, vegetable waste, like biomass waste per day, and he want to know what to do with it. Right now, he pay about 300,000 baht to discard those waste each month. But here he want to know if he can turn that waste into value, right? So that's the one problem that I would like one of the team to think about. Another problem, as I mentioned last time, Thailand, as we say, we are the stomach of the world, we are the kitchen of the world, but we don't have ammonia industry in Thailand. In order to grow plant, you need NPK, right? Phosphorus and potassium, maybe we can find it in Thailand, but ammonia right now all imported. So with the knowledge that we learn from artificial photosynthesis, making hydrogen, how can we make ammonia in Thailand? So that's the second problem I would like you to think. And the third problem is we are the country with a lot of island. And the island normally takes energy from diesel. So you have to import the diesel fuels into the island, and then it burn. Like Koh Tao, for example, they use a lot of diesel, and the EGAT over there, I mean, the electrical company over there, they just burn diesel and make electricity. So if you want to, make clean water and also clean energy, for the island of Thailand, that's gonna be very beneficial for the environment. That's the third one. And then another topic that I would like you to think is the country like Saudi Arabia, or UAE, for example, they're rich because they sell oil, right? But moving toward 2050, they want to reduce the amount of oil they sell. How can they stay rich? The answer is they need to be able to export renewable fuels. Instead of exporting fossil fuels, they need to be able to export renewable fuels. So I want you to think about how we can export renewable fuels from the desert. We can produce renewable fuel in the desert, which has sunlight but less water, right? Maybe more, maybe some near next to the seawater. So you can think about turning seawater into clean water and use for making hydrogen, for example. Yeah, how we can think about energy production from those area, because as I mentioned, we always fighting for the land, and we always want to make use of the land as productive as possible. So that's are the 4 topics. And what I want you to do is I want you to form the groups of 2 and then pick this, talk among yourself and then pick the topics. And then what we will do is we will have a project presentation on the last class. And before the last class, I would like to have the group by group supervision where you come and discuss idea with me. So toward the last class, maybe we meet about 2 or 3 times, schedule individual meetings, and then we develop the proposal, and then we develop the concept. Okay, and then toward the end we present. But you don't have to give me answer now. Just talk among yourself, and next week we will fix the group, and then we will start the process. Okay, so what is coming up next week is I want you to look at these photos, this scheme. So in order to do artificial photosynthesis, you need to capture carbon dioxide, right? You need resource. Carbon dioxide normally just spread everywhere. How you can capture it, that's the big challenge. Today we only talk about conversion. Right? Conversion, now we understand. But the other thing we have to think about when we look at this feasibility of this system is how we can separate and then manufacture the product that we want. And then how we can transport long distance, to different country. Maybe Thailand one day can be an exporter of ammonia, for example, or can be exporter of hydrogen. Because Thailand, if you look at it, we have a lot of space compared to Vietnam or other country. We have a lot of Lapum, we have a lot of space, right? How we can transport and then utilize and close this kind of loop. So this is what we're going to learn in the next class. And almost done. Okay, so this is the problem that I discussed before. Look at this again, and maybe you get more ideas about your final projects. Yep. Okay, that's it for today. Thank you very much. อ้าวอย่าบอกนะว่ามันหยุดอัด ไม่หยุดเนาะ How can we stop ฮะ
มองเหมือนอาจารย์สตอรี่สอนอ่ะอยู่
ไม่หายฮะแล้วทำไงอ่ะ มันหายไปแล้ว มันหายไปแล้วอะแล้วคนที่ไม่มาทำไงเนี่ยทำไงใครทำเป็นมั้งอ๋อมาแล้ว stop recording